I'm always curious about how crime analysis people like me can borrow analytical and cartographic techniques from other fields, geology, geography, even environmental science, and apply them to crime mapping in creative ways. These disciplines have long used elevation modeling and surface rendering to understand how terrain influences behavior. In this video, we'll bring some of those same visualization techniques into crime analysis by enhancing a standard kernel density function, or KDF, with hillshade and contour lines to create what's essentially a cartographic or topographical map of violence risk. We'll use shooting victimizations across the city of Philadelphia as our example. Before we get there, let's quickly review why we use kernel density in the first place. When you map individual incidents like shootings, the points often pile up in the same places, hiding the true intensity of activity. You can see clusters, but it's hard to measure how dense those clusters really are. That's where KDF really helps. It estimates the intensity of events across space, in this case the density of shootings per square mile, producing a smooth surface of risk. Think of it like this. Each shooting is a small drop landing on the map. It forms a peak at its center and then fades to zero at a distance we specify. When many of these peaks overlap, they merge into ridges and plateaus, a visual landscape of where crime risk accumulates. In this tutorial, I'll show how to enhance that surface using hillshade and contour lines to trace equal levels of intensity, turning your KDF into a quasi-3D elevation map. Then we'll confirm those density patterns with an optimized hotspot analysis, which tests whether those peaks and valleys are statistically significant. We'll start with a citywide analysis to see the big picture, then zoom into a single police district to make it more operational for day-to-day analysis. Before we begin, a quick note. The data you'll see represent real shootings, real people who were injured or killed. While our goal is to learn and improve public safety, it's important to remember that these aren't just points on a map. They're human lives. So as we analyze and visualize, let's do so with respect. To get started, I've created a project in ArcGIS Pro that contains two map frames. The first, visualized here, is a citywide analysis that includes the shootings in Philadelphia from 2015 through late 2025, and the city limits, which will be our bounding polygon. The second map frame focuses on the 22nd Police District, and it'll contain the shootings inside that area as well. And that's really so that we can conduct a more micro-level examination and kernel density and hotspot analysis of an area that's more operational for a police department. So we'll start with the citywide analysis. First thing we'll do here is activate the shootings, get a sense of what they look like and how many we are working with. When we open the attribute table, we'll see that we've got 17,288 shootings across the city. They mostly concentrate in the southwest Philadelphia area, Center City, and from north up into central Philadelphia, or central to North Philadelphia, and they become more broadly dispersed throughout northeast Philly. And you don't see too many shootings up here in the northwest, which is where Wissahickon Valley Park is located. So a couple of things I want to say before we start with this analysis. The first thing is that you need to make sure the layers you're working with are projected, because especially with kernel density function and with what we're going to do in terms of creating contour lines, you want to make sure that you're able to measure distances accurately. So use a projected coordinate system that works for your area. In my case, because I'm working in Philadelphia, I use NAD 1983 State Plane, Pennsylvania South, and that gives me a pretty accurate way to measure distance at a low level. So just keep that in mind, that you want to use a projected coordinate system. So the first thing we're going to do here is convert these points to a raster layer through kernel density function. The input layer, of course, is the shootings, or the point layer for shootings. We're not going to use a population field. We're going to call this kernel density or kernel ID citywide. I'd like to specify a 300-foot output cell size, and with a search radius of 25 100 feet, and the area units will keep to square miles. Keep in mind that with this analysis, our geographic area is fairly large. It's the entire city. So we'll specify a fairly large raster cell size of 300 by 300 feet. And when that happens, essentially the shootings will drop into each cell, and the densities will be calculated by the shooting points, and the influence of those shootings will extend outward to 2,500 feet in all directions. Once we have the parameters set up, we can just click Run, and as you'll see, it creates our new raster layer. So we'll deactivate the shootings and visualize the raster layer here, and you can see that it's not very compelling, honestly. We do see that pretty dark area, that high density area, right in the middle of North Philly, up near where the neighborhood of Kensington. When kernel density function first creates itself, its layer, it tends to symbolize based on the classify method, which I don't think is great for crime analysis. So I like to switch it from classify to stretch, which creates a much smoother across the geographic landscape with fewer abrupt ridges and areas from one end of the geography to the other. Before we go any further, I want to clip this raster to the city limits. And to do that, we'll use the mask tool, and it's technically extract by mask. It's going to take the cells of a raster that correspond to the area within the city limits, which is exactly what we want. So the input raster is our kernel density function. The feature layer will be the city limits, and we're going to name this something we can remember, KDF, and we'll just call it clipped. We want the area inside. And from here, we can just select Run. And once this is created, we can come over to our contents pane, get rid of the first one, and now we have a kernel density function that is clipped to the city limits. What I'd like to do now is play a little bit more with the symbology because I don't love this look. I'm going to come in to get something that kind of pops a little bit more. The stretch type here is %clip, which I like, and it's good for crime analysis, but we're going to switch this to exclude the bottom and top 2% of the density areas because this will get rid of the outliers for us and just create a smoother surface. And that's what the kernel density function looks like when we clip to the city and run it with the parameters that we have. This is a perfectly acceptable kernel density function. It looks good. We can get a good sense. If you look over here, for example, in the legend area in the contents pane, you see that the shootings per square mile range from 0, that's the purple area, up to that red area, which is 2,220.71 estimated shootings per square mile. That's quite a range, and it also looks good on our map. But we can go a little bit further than this by creating, under analysis here, a hillshade area. Let's click on the tools, type in hillshade. The input raster is our clipped KDF. The hillshade is just the hillshade. Now, the azimuth and the altitude are two interesting parameters that we have to deal with hillshade. Remember that hillshade creates a kind of elevation surface for us, and it's going to be based on the density ranges of the raster. That's going to act, again, as the elevation for us, and it's going to create a kind of hilly effect and a valley. Because it's hillshade, it's going to cast some shadows on that surface. And so we have to specify what those shadows are going to look like. And the first way is to set the azimuth. By default, the azimuth will be at 315 degrees, which means that a simulated sun will be hitting our landscape from the northwest, which means it'll be casting shadows behind it to the southeast. The sun's altitude will be 45 degrees above the horizon. These are both perfectly good parameters to use, so we're going to go ahead and leave those the way they are. For the Z factor, there's really good variation here, 0 to 2,220, so we don't need to multiply the Z factor by anything. We'll leave it at 1 and click on Run here. Once the tool finishes, it creates this kind of lunar-like structure, as you can see this. And what I like to normally do is drag the raster above the hillshade and then start working with the colors this way. The first thing I want to do is under raster layer, I'm going to make this density layer more transparent. I'm going to go to like 60% transparency maybe. That could be a little bit much. Let's start there, and then under blend layer, we're going to blend the colors together so that they create a more interesting architecture here. So I like to do darkening mode and multiply. That's often a good one for this kind of visualization. And I think 60 is too much. So why don't we go to 30% transparency? And this creates a layer that looks like it's three-dimensional, and the high density values are still in red. Essentially, this blending technique allows us to metaphorically drape our raster layer over the hillshade layer so that it preserves the densities, but also creates well, technically a 2.5 dimension visualization that simulates a 3D visualization. And this looks good to me, but we're not finished yet because now we're going to add our contour lines. The way to do that is click Analysis and then Tools. And this time we'll type in Contour. We'll click on Contours. The input raster, again, will be our clipped kernel density function. The contour interval for this will be 200 feet. That is, every 200 feet we'll basically get an elevation change. Base contour starts at 0, and we can just run this. Once the tool finishes, you'll see the new contour lines that, again, resemble elevation lines on a topographic map. I'd like to label these, though, so let's go into the contour area, and we're going to go to labeling properties. It's set to label the ID, so we're going to switch this to contour and apply. So now that we have the labeling properties defined, we can just turn on the labels. And there you have it. The one thing I'll say is the zeros aren't really doing anything for us. So typically what I'll do here is go into the properties and define a new definition query where contours are greater than 0. And once we do that, we have a much cleaner visualization. So if we come down here a bit, we're going to zoom into this map a little bit. Remember, our contour lines are at 200-foot intervals, and now we can get a pretty clear sense of what's happening here across the city. At the very top here, we see that we've got a shooting density. This one's probably 2,200 shootings per square mile. This next one out is 2,000 shootings per square mile, and so on down to 1,000. So this is a very descriptive map. It's also quite operational because it allows the analyst and the audience to get a clear sense of what shootings look like across the city. I'm going to go ahead and zoom out to the full layer. And now it's time to confirm whether or not these high density areas are significant clusters. And to do that, we're going to conduct an optimized hotspot analysis. Click into the hotspot tools, and obviously it's the shootings that we're going to use. Output feature class is hotspot analysis. We don't need an analysis field. And for the bounding polygons where incidents are possible, we're going to specify city limits, and we can run this. And here's our new hotspot layer. You can see immediately from the way the contour lines are laying over the hotspots that they follow very well the high density shooting areas. I'd like to declutter this visualization a bit by, at the very least, getting rid of the non-significant hotspot areas. And so to do that, let's go down to the GI bin fixed, and we'll say is not equal to 0, which are the non-significant grids, and click OK. And there you have it. We've got the significant hotspots and cold spots overlaying the city, which allows us to confirm that the areas of high density on the kernel density function are significant areas of high density, and that the blue spots are the cold spots. And as you can see, those are the lowest density regions as well. So it would be up to the analyst to figure out the best way to visualize this whole dynamic with the kernel density function, the hillshade, and the contour lines, and then overlaying the hotspots on top of those. Maybe it's a side-by-side map. Maybe it's something where the hotspots are a little more transparent, perhaps. But at the very least, the hotspot is a nice confirmatory technique that lets us know that what the kernel density function is identifying seems to be significant clustering. So now we're going to go into the second part of the analysis, which is to focus on the 22nd Police District in Philadelphia. To do that, we're going to come into the district, zoom to this layer here. Now, for those of you who know Philadelphia, you would know that the 22nd District extends into Fairmount Park here. The problem is the shootings in the 22nd District are mostly concentrated in the area east of Fairmount Park, and that's a good thing, green space, no shootings, but it would kind of skew the analysis if we ran a kernel density and hotspot analysis with this big area here. So what I did is I just went ahead and clipped this 22nd District to Ridge Avenue, and we're going to confine our analysis to that region. So this is a pretty micro level analysis, and we're going to do the same thing essentially in the same order. We're going to run the kernel density function and then create the hillshade and contour lines and then confirm what we find, hopefully, with a hotspot analysis. So the first thing we do is come under Tools. And by the way, if you have the crime analysis toolbar installed, you can just go right here and go right into kernel density function as well. So here our input features will be the shootings in the 22nd Police District. Here we're going to specify a 100 by 100 foot output area and a search radius of 1,500 feet. That means the kernel density fields are going to vary every 100 feet. The shootings that drop into those densities, they'll get their own intensity values, and their influence will decrease to 0 at 1,500 feet out. Remember, for the city level analysis, it was 300-foot cells with a distance threshold of 2,500 feet. So this is a smaller geography, and we're zooming into a much finer resolution. Area is going to be square miles, and we're going to switch over here to environments and tell the tool to limit the extent to just the clipped area, and then we can run this. And once it runs, we will deactivate the shootings, and we can see here already that we see more intensity with the kernel density function. We're going to go ahead and change this symbology just like we did the first time. We're going to change it to stretch just to get a better sense of what's going on here. It's a little less interesting, actually. And now we're going to clip it. Now that we've got the clipped kernel density surface, we can visualize that one. I'm going to go back and change the color scheme to something that I think is a little more interesting. And just like before, we're going to visualize this. The stretch type is going to be the percent clip, but I'm going to change this so that the bottom 2% and the top 2% of densities are going to be omitted from the visualization. And it's just a way, again, of creating a smoother surface across the whole geography. So now that we have the density surface, I'd like to create the hillshade layer. So hillshade, and the input raster will be the kernel 4, and the hillshade is there. And again, the azimuth is 315 degrees at an altitude of 45 degrees above the horizon. So we click run, and now we come back to our kind of lunar type surface. And again, I like to move the raster surface on top of the hillshade so we can kind of drape the raster over it. And we'll change this to 40% transparency to start with. And for layer blend, try again with the multiply. And that's pretty good. I can't tell if I like that transparency. Let's try 30%. What I like to do now is create the contour lines. Under Analysis, Tools, Contour. Input raster is the one we're visualizing now. We have the contours, and we'll set these contours to 100-foot intervals and go from there. And just like with the citywide analysis, we're going to label these. And first, we need to get rid of ID and label the contours. Click Apply. And this is the benefit of specifying the 100-foot contour intervals, because we get a much better gradient of densities of shooting. We range basically from 1,400 shootings per square mile quickly down to 1,000, and then you can see where it kind of goes down to 400 and out to 100. And we're going to run the optimized hotspot analysis now as the final step. Input features are the shootings. We don't need an analysis field. The bounding polygon will be the clipped 22nd district. And at this point, we can run it. Okay, once done. And as with before, we're going to get rid of the non-significant grids by simply creating a definition query where our values are not equal to 0. And that's what that looks like. And you can see that there's a pretty clear overlap with the hot spots and the cold spots and the high and low density areas of the raster layer. In fact, they overlap almost perfectly. If we turn off the hotspot layer, you're left with this quasi three-dimensional layer that gives important information about densities and shootings across this small geography. And that's the full workflow. We began by creating a kernel density function to estimate shooting intensity across Philadelphia. Then we enhanced it with hillshade and contour lines to visualize that surface as a kind of crime terrain. Finally, we overlaid an optimized hotspot analysis to statistically confirm where those high-density areas were truly significant. When crime analysts and police departments use maps like this, they're not just seeing dots. They're seeing where the underlying risk terrain of their jurisdiction reside. And that terrain can inform patrol deployment, prevention strategies, and even discussions with community stakeholders. I encourage you to try this for yourself, run your own enhanced KDFs, experiment with hillshade and contour lines, and see how your risk surfaces look. Then let me know in the comments how it came out or what insights you found. And as always, thanks for watching GeoCrimeHub, where we bridge the science of crime analysis with the art of mapping. If you found this helpful, hit like and subscribe, and I'll see you in the next one.